Welcome to my presentation on sustainable building materials, where I'm going to present how it is possible to develop houses made of concrete which are produced from the wastes of cassava production. My name is Schmidt, and it's a great privilege and a great honor for me to present today at the Berlin Science Week 2021. I work at the Bundesanstalt für Materialforschung und Prüfung, the Federal Institute for Materials Research and Testing, in the division related to technology of construction materials. And here, my specific research focus is on rheology, particularly particle polymer fluid interactions, which is required to better understand cementitious binders and chemical admixtures, where the research objective is always on increasing the materials efficiency and to find more sustainable materials and resources to produce high performance, high tech materials. And since rheology is in the center of my research, I'm also the secretary of the German Rheological Society, but at the same time, I'm always trying to convert this research into more societal relevant aspects. And therefore, I'm also officer in the Bureau and the Development Advisory Committee of RILEM. RILEM is an international network of experts and laboratories in materials. And here I'm also the convener for Sub-Saharan Africa. And together with RILEM, I've been heavily involved in the development of the global consensus on sustainability in the built environment, which can really become a game changer because all the relevant associations which are dealing with pre-normative developments and research who have a big impact in the world are involved. They take over the responsibility, but also the initiative to change something in the future. And this sustainability research has also been a company to me over the course of the last 12 years when I had started to collaborate with researchers from all over the African continent in laboratory collaboration, but also educational activities and a lot of research activities. And within this framework in the year 2018, together with my colleague, Dr. Kolawole Olonade from the University of Lagos, we were awarded with the German African Innovation Incentive Award by Federal Minister Anja Karliczek. But this is not the only part of the research. There has been a lot of collaboration with people from all over the world, all related to more sustainable, more equitable concepts for the development of urban environments based on materials, but also on structures and so on. And some of these collaborators are mentioned here, not all of them, but these people have had a big impact on my research and also the slides I'm going to show now. But now, without further ado, I would like to come to the challenges of the 21st century, to the core of that talk, where we can see that at least from a technical and from an environmental point of view, these are the most challenging ones, and these are habitat, infrastructure, urbanization, environment, and resource depletion. And if we take a closer look at these 5 challenges, we see that concrete plays a major role in creating these challenges. Because concrete is nearly half of everything that human beings produce. After water, it is the second most consumed good on Earth. Concrete is everywhere. And we know that the entire built environment contributes to about 40% of the total global carbon emissions, the construction industry for more than 10%, and the cement production alone for about 8%, 5 to 8%. So these are dramatic numbers where you could really get desperate. But on the other side, you can also see if there is such a huge global demand and this material is required also in the future, if we change something in a material which is required all over the world, we also have the power to change something, because that is a huge leverage to really have an impact. But the problem is, concrete has a very, very negative perception in our society. Bob Marley already sung about the concrete jungle, where he sang, "No chains around my feet, but I'm not free. I know I'm bound here in captivity in this concrete jungle." So it really doesn't have a very good reputation. And indeed, if we take a look at certain structures and certain quarters in our cities, we see this really resembles a concrete jungle. But is it really the fault of the material, or is it the fault of the architect? Because there is also wonderful architecture which has been implemented particularly by the strength of the material which is called concrete. Therefore, we always have to take a look at those materials that can really be used for our urban structures, those mass materials, which all have their pros and cons: earth materials, timber, steel, concrete. So we have to ask ourselves, why do we have to use concrete at all? And the simple answer is that cementitious materials are the only materials that can really meet the demand. Here in this figure, you can see the production of cementitious materials all over the world in comparison to other construction materials, and you can see that it's just an order of magnitude higher than everything else. And the production certainly also represents the demand on Earth. And that means concrete is really the only material that we have on our Earth to meet the demand of the growing population to live in urban environments. It also means it's the material that will continue to build our cities. And we also have to see that concrete is not as bad as its reputation. In this figure, you can see on the ordinate, the embodied carbon emissions, and on the abscissa, you can see the embodied energy. Concrete is here. Cement certainly has a relatively high carbon emission. Any other materials, including timber, are higher in value, which means if we would replace concrete for any of these materials, we would just make the situation worse than it is already. And we also have to see that, yes, it's true, concrete is responsible for about 10% of the global carbon emission, cement alone for about 8%, but we also have to see that concrete is nearly half of everything that human beings produce. And in this light, these 10% are not the worst. And another aspect that makes concrete absolutely inevitable is that the chemistry, the elements that are used to produce concrete are exactly those elements that make out 98% of the outer Earth's crust. That means the chemistry of our planet also determines which materials to use, and that in this case seems to be concrete. We just have to look at different sources to find these elements. So concrete is inevitable. Whether you love it or whether you hate it, it doesn't matter. There is no better alternative to concrete. But the good news is there is a slightly better alternative, because we can make this concrete greener, more sustainable by using more sustainable cement types, by using better concrete types, and also by using less cement and concrete. And another aspect, which I'm not going to elaborate on today, is that we also have to develop structures that require less materials, or that use materials at its best performance ability. So there is a special African challenge. I mentioned that already before a couple of times, and that is the urbanization. We have to see that the urban population grows all over the world, or has been growing all over the world, and it seems the trend continues. But particularly in Africa, this growth has been dramatically higher. And as a result of that, in the future, we will have megacities in Africa, which the world hasn't seen before. 13 out of the 20 most populated cities in the world in the year 2100 will be on the African continent. And we will have cities like Lagos with 88 million inhabitants, Kinshasa 83 million inhabitants, Dar es Salaam 74 million inhabitants. And these are challenges that are unprecedented. And the good thing about it is that of those structures, and these numbers are until the year 2050, of all those urban structures that will have been built until the year 2050, only 20% already exist today, which means we are going to build 80% of the urban structures in 2050 over the course of the next 30 years. And 30 years, considering a construction process, is really not long. So we don't have the time to spend on, okay, first we have to do this, and then this has to come, and then this has to come. If then solutions are not an option, we have to act now, and we have to act all. And that means we have to develop greener mass materials already now. Certainly there are technologies like carbon capture and storage that can contribute to a greener environment, but we cannot wait for that. We have to use the solutions that already exist today. And now let's talk about the innovation potentials in Africa. And therefore, maybe it is important to first see how concrete traditionally works. We use cement, which finally, as a reaction with water, forms the cement paste, which is the binder for the sand and the aggregate, which are mixed with it. Now, in order to make concrete greener, to reduce the carbon footprint, we have to minimize the amount of Portland cement clinker that we are using in our binder and replace it by so-called supplementary cementitious materials, which have a lower carbon footprint. And in addition, the more water we add to concrete, the lower the strength and the worse the durability will be. So we have to find ways to minimize the water content in concrete, and that requires chemical admixtures. Also, these chemical admixtures can contribute to compensate for some negative aspects, particularly with regard to workability of those supplementary cementitious materials. So we have the supplementary cementitious materials as one part of the solution, and to understand how they work, it's necessary to understand that cement and water react, and immediately upon contact, all kinds of reactions take place at the same time. And these reactions are very complex, and new phases are formed and dissolved, and adsorption takes place, crystallization processes, dissolution, precipitation, and so on. And the type of reactions that take place depending upon the chemistry of the cement are very complex, and they can have all kinds of effects depending on the application as well. But the most important phase is the reaction of the calcium silicate hydrate phases, because these calcium silicate hydrate phases provide strength to concrete. And pretty much linked to it, there is the formation of calcium hydroxide, which has certain properties, which provides certain properties in concrete, but mainly does not contribute to the strength of concrete eventually. And this is the point where the supplementary cementitious materials, particularly the pozzolanic materials, come into the game, because these pozzolanic materials, they react as a secondary reaction with the calcium hydroxide. And this reaction forms supplementary calcium silicate hydrates, which give additional strength to concrete. And this additional strength potential can help us to reduce the cement, the overall cement, or the Portland cement clinker that we're using in our binder. Now, the other part I was talking about, when we use chemical admixtures, we have to see that in a traditional concrete where there's no superplasticizer used, cement and water are added for the reaction to form, for example, calcium silicate hydrates. But unfortunately, the water amount that is required for the reaction is too low to provide a good workability of the concrete. So even though we could theoretically achieve a high strength, when we cannot compact it, we cannot really use it. So we have to add excess water that provides workability, but when this excess water, which does not react, evaporate, it forms pores, and that reduces the strength of concrete. Now, if we are using superplasticizers, they adsorb on the surfaces of particles and increase the workability without adding water, so we do not need excess water. And with these superplasticizers, we can really increase the strength, and by increasing the strength, we can reduce the overall cement amount that would be required. So both works in parallel. We've got these two strategies. We can save cement by reducing the clinker content, but in order to make the entire concrete greener, we have to find novel replacement materials like calcined clays, for example, or what I'm going to present about, waste materials. And the other strategy is to reduce the overall cement in concrete by using chemical admixtures. But these chemical admixtures today are typically based on crude oil. They are heavily processed. They have a lot of transportation throughout the world to become precursors as first, then chemical products, and then reach the applier. So there are also alternatives which we have to look at, which avoid the use of crude oil-based chemistry. And these alternatives, particularly on the African continent, exist. Cement replacements can be bio-based, like the ashes from maize cobs or rice husks. sugarcane bagasse or cassava peels, groundnut peels, and so on. And for the chemical admixtures, we also have plenty of nature-based alternatives, so-called polysaccharides, which are sugar-based polymers, like acacia gum, like certain gums which are inside of the bark of various species, cassava starch, cocoa wastes, and so on. Now let's first talk about the potentials of the bio-based cement replacements, where I made a survey of different countries and I compared the amount of available bio-based waste resources to the overall country's cement production capacity. And we can see that we can replace something between 1 point something and 5.9% of the overall cement production capacity. That, first of all, doesn't sound too much. But you have to see that in most countries, the total cement production capacity and the real cement production diverges differently. So the real cement production is often just half or a third of the overall capacity. So we could already multiply these values by, let's say, 2. Then we have to also consider that the yield per hectare in many African countries is very, very low, and it could be increased by a factor of 4 to 8. So then we can already multiply this already before multiplied value by, let's say, a factor of 4. And then we also have to see that the agricultural production one-on-one correlates with the population growth. That means there will be more and more of this agricultural waste is coming up in the future. And we have to consider that the African continent provides about 60% of the unused arable land areas of the entire world. South America, by the way, another 30%. So the vegetation in South America is very similar, and these concepts could also work in South America. That means there is a tremendous growth potential. And if we multiply this by the factors that are possible, in the future we already reach values which are higher than those cement replacements we are using today, like fly ashes or ground granulated blast furnace slag, at least in some countries. So there is a tremendous growth potential for bio-based wastes to become resource for cement production. And now if you talk about the bio-based chemicals, the answer is relatively simple. We have plants growing all over the world. They all provide all kinds of polysaccharides, of sugar-based chemistry. We do not even have to think about it. There's potato, cassava, maize, wheat, whatever. We always find plants with polysaccharides that have very positive contribution to cementitious materials. And finding alternative cementitious binders and ways to optimize the performance of the cementitious binder is of utmost importance in sub-Saharan Africa. Not only to contribute to a greener environment, but also to contribute to better livelihoods and lower prices, because reducing the prices for cement is extremely important. Here on this figure you can see the number of working days an average income worker in the countries which are shown here has to work in order to purchase 1 ton of cement. And you can see that in the United States or in Germany, an average income worker would have to work for half a day. So I could easily pay this out of my wallet without feeling too much pain. But in the Democratic Republic of Congo in the year 2009, an average income worker had to work for 323 days, nearly a year, to purchase 1 ton of cement. And now the situation has become a bit better, but we still talk about nearly 150 days. So everything that helps to reduce the cost of cement also contributes to better livelihoods, to a better economy, and also to more equitableness in the region. So here, this is a very good example how a contribution to better climate also contributes to better markets. And in order to underpin this, I would quickly like to show you this case study where we developed circular high-performance concrete value chains made of the wastes of cassava. And cassava, which is also known in other parts of the world as mandioca or yucca or tapioca, is a very important plant on the African continent. On the left side, you can see how the production grew since 1961 in light blue until 2014, and you can see the trend continues. In South America, it stagnates, and in Central America, it's kind of negligible. But in Asia, also, you can see there's a growth, but it's not as heavy and not as steady as it is in Africa. Nigeria alone produces about 20% of the global cassava production. And Sierra Leone and Ghana are those countries which have the highest per capita production of cassava. And here you can see what I've mentioned already before. You can see the population growth in Nigeria, and you can see the growth of the cassava production in the country. And you can see there's nearly a one-on-one correlation, and that I think applies for quite many countries. And cassava is a very gentle plant which grows on also on unfriendly soil, and it's very tasty and it's very well nourishing, and you can produce a lot of good food made of cassava, like fufu or gari and other types of food, which I really have started to love. What is happening today that the cassava is being harvested, and then the thick peels are cut off. Mostly there's a lot of starch still adhered to the peels, and then the inner part of the tuber is converted into a food product. And since the peels are not easy digestible for animals, sometimes they're even poisonous, they cannot be used for animal feeding. Goats would eat it if you blend it with some other constituents, but mostly these wastes have no use today. People typically just dump it away where they rot away, where they start to stink, where they pollute the groundwater, and where they require a lot of space, which could be used in a better way than just dumping rotting bio-based materials upon it. And instead of considering that as a waste, as a useless waste, it's possible to first derive the easily soluble organic components, mainly starch, from these waste peels and convert it into a superplasticizer to reduce the water content in concrete, and this way to tickle out more performance of the cement, and this way save overall cement in concrete. And then the residual peels, after obtaining the starches, can still be burned. There's still a high organic component if you do it the right way. In the first step, you can go for a pyrolysis, or you can do it without carbon emissions and obtain additional precursor components. And after that, you can still burn it and derive ashes which have cementitious properties. So these ashes can be used to replace Portland cement clinker, which is much higher in carbon footprint, and this way additionally contribute to better climate. And the positive thing about it is that it's not only contributing to the climate, but it also creates new value chains. And these value chains are local value chains. So from something which formerly has been just a food product, now with the wastes of this food product, it's possible to create a chemical value chain for chemical admixtures that help reducing the carbon footprint, and another value chain where energy is produced and cementitious binders are produced for mortar, or for dry mix mortar, for example, or as a cement replacement, or for concrete production. And these are all local value chains, which also help the regions in which cassava grows to economically grow. And since people typically do always not really believe in that, although chemically we understand very well what's happening here, I would even dare to say that's not even new, because we have been using fly ashes, microsilica, ground granulated blast furnace slags in the past. And here we're using the same chemistry, we are just using a different resource, in which people often do not trust, because people always believe if it's a bio-based resource, it probably qualifies for low-tech or for low-end construction, and which is not true. It's just really a different source, and in order to make it more tangible that it really works, currently we are building up a small structure made of cassava-based concrete. This structure is currently being built. Due to COVID, everything has been significantly delayed, but now it's happening on the campus of the University of Lagos, and I hope that in the next year this structure is finalized, supported by the Federal Ministry of Education and Research. And the contribution is not only better construction technology, but it has a much more global scale, Because today the livelihoods in the rural environment are decreasing. Rural environments deliver farm products to the cities, but the prices are going down, the competition is increasing also internationally. So the livelihoods for rural farmers are not very good. But instead of just delivering food products to the cities, in the future it's possible to also use the wastes and convert them into materials, into chemicals, and into energy and additional chemical components. And these can be used for urban construction materials, specifically concrete, which also creates new employment perspectives in the urban environment. And this way, money flows back to the rural environment and the urban growth. This way directly contributes also to the development of rural areas. But there's certainly a challenge. We have to work on concepts, how we can create rural to urban circular value chains and rural to rural circular value chains and urban to urban circular value chains. And everything depends on the environment, on the supply chains, on transportation distances, on the quality and the quantity of materials, which means whatever decision you take, how to further the process to the next step, there are a lot of decision-making processes in between. And the best practice varies from place to place. So there's not one way, there's only a best practice that is specific to a specific environment. And that requires that people talk to each other and understand the different challenges. And this directly brings me to the conclusion. If we have so many best practice solutions which are specific for different regions where decision making is so complicated and requires the knowledge of so many people, we have to work together more in an interdisciplinary way, where the different experts from the different disciplines, from chemistry to colloidal physics, inorganic chemistry, materials, mineralogy, civil engineering, work together and bring these concepts into the right context and derive solutions which are specific for the individual situation, which are always the best at the end of the day. But not only interdisciplinarity is important, but also inclusiveness. Today in the engineering area, there's still a lack of female participation. And what we require is that we find the best talented people to work on the best solutions. But we cannot continue to just recruit the best talented people from the male pool. There's another pool, 50% of female population, that has the same number of talents. So we have to bring these talents together and work together hand in hand. And this is one of the reasons why I'm currently involved in the Female Academic Leadership Network for Conscious Engineering and Science Towards Sustainable Urbanization, www.falcones.org. This is of highest importance. And what is also important is that we find new ways to teach our future decision makers. That requires that we derive engineers in the future that also have an understanding of the beauty of nature, of history, of markets, of the micro scale as well as of the global scale. And that also means that teachers, professors, and students have to work much more together to derive the best possible solutions, because the professors, they do have the knowledge, they have the wisdom they can give to the students, but the students, they have the nowness and they have the affinity to novel technologies and innovation. And therefore, students and professors have to mutually lift themselves up to higher levels to become more conscious and derive the best possible solutions. And that means also that today's decision makers should not work among themselves, but they should already start to mentor the next generations, the students and the school children and even the smallest children. But it's not enough to just mentor them. We also have to listen to them, because these are the people who are affected the most of our decisions today. So we have to listen to them and we have to learn from them. And then only we can be able to derive the best possible sustainable solution. And therefore, I would like to give the last words to a child, Josephine.
My name is Josephine. I would like my children to have more freedom and live in a simple house, built with materials which don't destroy the environment, and has enough space for my kids to play.
And with that, I would like to thank you very much for your kind attention.